Hi, and welcome to lesson 4.6. We're going to be using quadratic functions to solve problems. And before we do that, we're going to have a look at quadratic functions in factored form, which we haven't seen yet, but they're going to be really useful in solving these problems. It's going to save us a lot of time. Okay, so first thing, notice that we don't have anything squared. If I were to multiply that all out, I would end up with x squared plus something x plus something. We're not really that worried about that right now. What we do want to know, though, is where the x-intercepts are. You remember the x-intercepts happen when y equals 0. So if I set 0 for y, I get this. Notice that if x equals 1, or if x equals 5, the right side will equal 0. So these are going to be, let's see, we can actually put these on here. So there's x equals 1, x equals 5. So we've got 2 points now. And if I put them on here, 1, 2, 3, 4, 5, and then I can throw in a 0 and a 6 as well. And we know that y equals 0 when x equals 1 or 5. Now I can just plug in 0, and I'm going to get negative 1 times negative 5 gives me 5. Plug in a 2, it'll give me a negative 3, negative 4, negative 3, and 5. So here are the rest of our points here. And there is our parabola. All right. So notice that when we're in factored form, main thing that's going to come out is when we find out when these things are 0, that'll mean the entire right side is 0, which means that we'll have an x-intercept. Okay, notice this one's exactly the same except for we've got a negative 2 here. So we know our x-intercepts are still 1 and 5. And let's do the same table. And we know that's going to be a 0 and that's going to be 0. This time if I throw in 0, I'll have negative 1 times negative 5, which is 5. But then 5 times negative 2 will give me negative 10. So that'll be 6, that'll be 8, 6, and negative 10. So that'll be negative 10 down there. 6, 8, 6, and down to negative 10 again. So notice that this negative 2 is still my vertical stretch factor. It's just that the same as it was before when our vertex was on the x-axis, we're still stretching away from the x-axis. It just happens that it's a different point on the parabola that's fixed on the x-axis. Okay, so notice, so last question asks us, what's the same? Well, our x-intercepts are the same. What's different? We've been stretched away from the x-axis in different ways. So the negative makes this one open down instead, the same way as if it was negative on the other one, and it's stretched twice as far vertically, the same as it would be if the stretch factor was in vertex form. Okay, so let's see how easy this can make our lives here. Oops, that's not the pen I wanted. So let's just draw a rough sketch of this graph first. It tells us our x-intercepts are at 1 and 7. And the function passes through 3/16, so that's going to be somewhere around here. Which means our parabola must look like this. And I just lost my 1 and my 7 a little bit, so I'll rewrite them there. Okay, so if we're going to write this in factored form, we won't know our vertical stretch factor, our a, but we will know that there must be an x minus 1 here because we have an x-intercept at 1, and this must be x minus 7 because we x-intercept at 7. So now if we just take this point, sub it into there, we can really quick, easy figure out what a is. So we'll have 16 equals a times 3 minus 1 times 3 minus 7. So I get 16 equals a times 2 times negative 4. So 16 is going to equal negative 8a. So a is going to equal negative 2. So they want us to write the equation. So here's our equation. Y equals negative 2 x minus 1 x minus 7. Okay, so notice that that's going to mean we've got x-intercepts at 1 and 7, and we've got a vertical stretch of 2 away from the x-axis, opening down. Okay, so this is a very similar question, except for they've added the idea of a bridge in here. So the bridge is going to span a distance of 40 meters. So it's, oops, still on the highlighter again. So the way I'm going to do it is I'm going to put points at 0 and 40. You don't have to put them here. I just think it's one possible useful way to do it. You could also go on negative 20 and 20. Would have been relatively simple. I mean, if you wanted to, you could do like 11 and 31, which would make no sense. Okay, and it's parabolic arch, 1 meter from the end of the bridge. The arch is 1.95 meters high. So here at 1 meter, that'll be 1.95. So we'll have a point there. So we're going to be doing that. And that is a terrible parabola. Okay, so same as last one. Y is going to equal a. If you want to think about it, you can write x minus 0. It's just x. But if it helps you think about it that way, you can write x minus 0. You get x minus 40. And we've got this point here of 1.95. So let's just rewrite this a little bit neater here. Ax. X minus 40 is our equation. And we're going to plug in this point 1.95. So that'll be 1.95 equals a times 1 times 1 minus 40. So that's going to be, let's just zip up here. 1.95 equals, well, 1 minus 40 is negative 39 times 1 is just going to be negative 39. A, so divide both sides by negative 39. And apparently we're working in decimals, so we end up with a equals negative 0.05. So our equation is y equals negative 0.05 x times x minus 40. B wants to know how high the center of the arch is. The center of the arch is going to be at x equals 20, because we know our vertex is going to be on the axis of symmetry, which means it's going to be halfway between the two x-intercepts. So I'm just going to take my equation and throw in 20. Oops. And I'm going to end up with y equals 20. So the center of the arch is 20 meters high. Okay, maximizing and minimizing. Notice that on all our graphs, we're always ending up with a maximum or minimum value of y. So it makes sense to define whatever variable you're trying to maximize or minimize as y. So in this case, we're trying to maximize or minimize the sum of the squares. So we'll say that y is the sum of squares. And then we've got two numbers. So I'll say x is one number, and I'll say y equals the other number. Sum of squares means that y equals x squared plus z squared. And they've also told us that the two numbers have a sum of 20. So x plus z equals 20. Okay, to combine these two, I'm going to use substitution. So I'll subtract x from both sides here. Get z equals 20 minus x. So that will give me y equals x squared plus 20 minus x squared. Remember that 20 minus x squared is 20 minus x times 20 minus x. So that'll give us 400 minus 40x plus x squared. So to rewrite that in a little better form, y equals 2x squared minus 40x plus 400. Okay, you'll find on this one, you can spend your whole life trying to get this into factored form or find an x-intercept, and it is never going to work. And we'll find out why when we get to the end. But yeah, this one we're going to have to do the old-fashioned way of completing the square. So before we can complete the square, we need to get rid of this 2 in front of the x squared. So let's divide everything on both sides by 2. And I'm going to leave a nice big space here. So y over 2 is going to equal x minus 10, because 10 is half of 20. And then 10 times 10 is 100, so plus 100 minus 100. So that's going to be plus 100. And now we need to multiply that 2 back through both sides. So that gives us y equals 2 x minus 10 squared plus 200. Okay, and let's just have a quick look at what our graph is going to look like then. So we're going to have a vertex of 10, 200. So that's going to be 10, that's going to be 200, and we're opening up. And now you can see why it wouldn't be possible to use the factored form, because we don't have any x-intercepts. So there actually is going to be no factored form. There's no possible way that this quadratic function could factor. Okay, so we're gonna means we know we've got a minimum of y equals 200 when x equals 10. So thinking about what that means, according to the way we defined our variables, we remember that y is the sum of the squares and x is one of the numbers. So sum of squares has a minimum of 200 when the numbers are, well, one of the numbers is 10, and if they add up to 20, then the other number is going to be 10. So we'll have sum of squares have a minimum of 200 when the numbers are both 10. Okay, last question. We've got a farmer, has 100 meters of fence, wants to make a rectangular pen. What dimensions will maximize the area of the pen? Okay, so first off, we're going to define y as area, because that's the thing we're trying to maximize. And then I'm going to define my other two variables as x and z here on the diagram. And we're going to know that y is going to be length times width, so y is just going to be x times z. And total amount of fence is 100 meters, so I'm going to need 2 x's and 2 z's to add up to 100. Can divide both sides of that by 2, make things a bit simpler. I get x plus z equals 50. And now I'm going to combine these two by substitution like I did on the last page. So minus x from both sides. I get z equals 50 minus x. Sub it into my area equation, and that is going to give me y equals x times 50 minus x. And this is nice. This is actually already in factored form. One thing I'm going to do is I'm going to factor a negative 1 out of this 50 minus x just to make things look more familiar. So we'll end up with y equals negative x times x minus 50. Okay, which means we have a pretty good idea what the graph's going to look like. We're going to have an x-intercept at 0. We're going to have an x-intercept at 50. And we're going to be opening down with a normal shape. Well, our maximum is going to occur here, at 25. because it's halfway between 0 and 50. So our maximum will be y equals negative, 25. 25 minus 50. And that gives us y equals 625. So we know that this is 625. So we've got a max of y equals 625 at x equals, what's going on with my pen? There we go, we got the pen working again. So 625 at x equals 25. And according to the way we defined our variables up here, that means that we're going to have a max area of 625 meters squared. And that's going to happen when that side's 25 meters, which means that that's 25 meters. So we've used up 50, so we have 25 left for each side here to total up to 100. A good check in the end with this is we can go 25 times 25 does give us 625. Notice a square is a special case of a rectangle, for those of you saying that that's not a rectangle. Okay, so notice that when we can use it, factored form when solving problems like these can make our lives way easier. If you have a hard time using the factored form, all of this can be done using completing the square with a bit more work. But if it makes you feel more comfortable, you won't lose any marks by using completing the square. And there is a video of all of these questions being done by completing the square.